Parts of a wave. So we're going to be looking both at the transverse wave, which is something that you're more familiar with, and a longitudinal wave. So examples of transverse waves are things like ocean waves, or what we do with our slinky when we're waving it back and forth, a jump rope. Light also, we say, travels in a transverse wave. So there's certain aspects to it. You have the highest point, which is called the crest. It's also called an antinode. That's the part that moves up and down the most. You have the node, which are the parts of the wave that never move. So think of them as the handles in a jump rope. Technically, those parts don't really move. It's the jump rope that's moving up and down like this. And the part where the people are holding it doesn't really move. Those are the nodes. And then you have the trough. So if I have what's called a standing wave, which is basically something that's moving back and forth, like a jump rope, from the outside, it will look like basically series of ovals put together. The amplitude is the highest from the node to the crest or the node to the trough. So think of it as the hand position to the lowest position of the jump rope or the highest position of the jump rope. And then the full wavelength is going to contain one full crest and one full trough. So it can be from here to here, here to here, here to here, or if I had another trough, here to here. Any combination, as long as in total you have one full crest and one full trough. The other type is called a longitudinal wave, and this happens with sound waves, shock waves, earthquakes. Earthquakes actually can have both longitudinal and transverse waves, but basically it's if I'm taking my slinky and I'm moving it back and forth like this, I'm going to have areas where I'm compressing the spring and then it opens up again, compress and open up. And the areas of compression are easy to see. And then what we have when they open up is what we call rarefaction. And that's when they're most expanded. The amplitude is a little harder to see, right? It's not like you can say, oh, here's my node and my crest, but basically it's how close I'm compressing it versus the relaxed state. So it's basically how much it goes from compressed to open, about half of that amount. And then one full wavelength is going to be including one full compression and one full rarefaction. So it can either be here, from here to here, from here to here, here. It doesn't matter as long as you have one full compression and one full rarefaction. That's a wave. You can also have a pulse. Some of our experiments that we do, we're going to have pulses. And a pulse is just basically where I'm flicking it up and down, or I'm pushing it just one crest or one trough or one compression, and you're following that all the way through, and then it can either be reflected back or whatever. So this would be what it looks like over time. If I have a crest, it's moving this way. If it was a trough, the trough will move, or I can have one full wavelength where it goes up and down. So a pulse is just one of these traveling along a string.